Let us first of all try to understand the concept of electric current. As we mentioned, electric current means current electricity. Current means flow and electricity means electric charge. So current electricity deals with the flow of electric charge. This flow of electric charge may take place anywhere in the universe. It may take place in open space as in case of lightning, or in the region inside the conductor as electricity flowing in the wires. Here in this chapter we will limit our discussion to the flow of electric charges in the interior of conductor under the influence of electric field. This electric field arises when the ends of the conductor are connected to the terminals of a battery. Electric field exerts force on free electrons inside the conductor and causes them to travel from one end of the conductor to the other if electric field is applied along the length. This gives rise to electric current in conductors. In the present slide, students, we will be discussing electric current mathematically. Mathematically, electric current is defined as the rate of flow of charge, or the amount of electric charge flowing through any cross section of the conductor per unit time or per second. So if Q is the electric charge flowing through any cross section of the conductor in time t, and if the flow of electric charge in the conductor is uniform, then I, electric current I, is equal to Q by T. If the flow of electric charge in the conductor varies with time and dq be an elemental charge flowing through the conductor in time dt, then instantaneous charge electric current through the conductor is given by I equals to dq by dt. Let us now discuss different types of electric current that can exist inside a conductor. Let us see this graph. The first type of electric current represented by the graph is the current that does not vary with time, or steady current. The second and the third graph represents electric current that varies with time. The third type of electric current is also electric current that varies with time, but the variation is periodical. Such electric currents are called as alternating currents. In this slide, students, we will be discussing about the concept of conventional current. As you can see, there are positively charged particles flowing from the positively charged plate to the negatively charged plate in the figure alongside. Conventional current is the current whose direction is along the direction of the motion of positive charges under the action of electric field. In the second figure, you can see the flow of negatively charged particles taking place from negatively charged plate to positively charged plate. This current has a direction exactly opposite to the direction of conventional current. So if current is due to the flow of electrons, conventional current has a direction opposite to that of motion of electrons. The next topic we will be discussing is drift velocity and electric current. We shall be providing a detailed description or the detailed discussion of drift velocity in the coming slides. The figure shows a cylindrical conductor, the ends of which have been connected to the terminals of a battery. You can see that the electric field existing inside the conductor is E. Due to the force exerted by this electric field, the electrons move from the end of the conductor connected to negative terminal of the battery towards the other end, which is connected to the positive terminal of the battery. The arrows represent the direction of conventional current. Here I am providing a few equations that provide the relation between the quantities under consideration. These relations will be discussed in great details in the upcoming slides. In this slide, students, we shall be discussing the actual mechanism of flow of electric current in a conductor. In an electric conductor, the motion of electrons, free electrons, can be compared to the motion of gas molecules confined in a container. We know that gas molecules confined in a container are in a state of constant random motion, and they move in all possible directions with all possible velocities. Similarly, the free electrons inside a conductor also keep moving freely in all possible directions with all possible velocities. Their motion is completely random and they keep on colliding elastically, continuously and frequently with each other as well as with the fixed atomic cores in the crystal lattice. Since the motion is completely random, there is no net flow of charges in any direction. That is why the electric current inside the conductor is always zero in the absence of any external electric field. When electric field is applied, the electrons start experiencing electric force in particular direction opposite to the direction of electric field. This causes electrons to accelerate opposite to electric field. The random motion due to thermal agitation continue to take place. Now, as a combined result of action of random agitation and the force exerted by electric field causes the electrons to drift slowly from one end of the conductor to the other. At macroscopic level, the acceleration of the electrons is never visible. This is because the path of the electrons between two consecutive collisions is very short. So they seem to be moving from one end of the conductor to the other with a somewhat constant velocity. This velocity is called drift velocity. In this slide, students, we shall be discussing a very useful result. This result finds its utility in the mathematical expression for drift velocity. Even when electrons move under electric field, after every collision, the direction of motion is unknown and the energy that is gained from electric field is completely lost. So immediately after every collision, the motion remains completely random. Since the motion remains completely random, so the vector sum of velocity of all the electrons just after collision should be equal to 0. Remember that if the motion of a large number of particles taking place in some confined region of space is completely random, the vector sum of velocities of all the particles always remains 0. This result is also applicable for the case of gas molecules moving randomly while confined in a container. So immediately after collisions, the vector sum of velocities of all the free electrons must also be equal to 0. Now students, we will try to develop understanding of two important concepts and provide their definitions. These two concepts are those of relaxation time and drift velocity. Let us first of all begin with relaxation time. When electrons move under electric field, they undergo frequent elastic collisions with each other. The time interval between two consecutive collisions is not the same in general for any two electrons present inside the conductor. However, if we find out the average of time interval between two consecutive collisions for all the electrons inside the conductor, we will see that this average value is always constant and depends on the temperature of the conductor only. This average time interval between two consecutive collisions for all the electrons in the conductor is called relaxation time. It is denoted by Greek letter tau. Let us come to drift velocity. We already had a theoretical discussion of the drift velocity in the previous sections. Here we shall be providing a brief definition and a mathematical definition of drift velocity. The average constant velocity with which electrons move from one end of the conductor to the other under the influence of applied electric field is called drift velocity. Mathematically, we define drift velocity as the average of velocities of all the electrons in a conductor immediately before their collision with the fixed atomic cores when they move under electric field. From this slide, we shall be carrying out mathematical description of this chapter. We will begin with the relation between drift velocity and relaxation time. Suppose a cylindrical conductor of length L has a battery connected across its ends. Suppose E vector be a uniform electric field that arises inside the conductor because of applied potential difference. If minus E be the charge of an electron, then the force F vector acting on each electron is given by F vector equals to minus E multiplied by E vector, which is electric field. Let us call this equation as equation 1. As a result of force, acceleration results. So acceleration A vector is given by force by mass. This gives equation 2. Because acceleration is uniform, so for the motion of electrons, we can write down the kinematic equation V vector equal to U vector plus A vector multiplied by T. We are discussing the motion of any particular electron between two consecutive collisions. So U vector is the velocity of any arbitrary electron after collision, and V vector is the velocity of the electron just before the next collision. A similar equation as equation 3 can be written for all the electrons moving inside the conductor. Writing down n equations for all the n electrons present inside the conductor and adding up all the equations, we get the result as sigma V vector equal to sigma U vector plus A vector sigma T. We divide both sides of this equation by total number of electrons n inside the conductor. Substituting the value of sigma U equal to 0, we get sigma V vector by n equal to A vector multiplied by sigma T by n. By definition, the average quantity on the left hand side is the drift velocity of electrons, and the average quantity on the right hand side, sigma T by n, is the relaxation time tau. So the final expression for the drift velocity is Vd vector equal to minus small e into capital E vector by m multiplied by tau. Here we must understand why sigma U should be equal to 0. Just after collision, the motion of electrons is completely random. We have discussed this in the previous section. And since motion of electrons just after collision is completely random, so vector sum of their velocities just after collisions should be equal to 0. So we get the final expression for drift velocity as given in the box.